Dielectrics. A dielectric is any material that is not a conductor itself, but polarizes really well. Even though they don't conduct, they are electrically active. So putting a dielectric material in a uniform electric field causes a dipole moment to be induced on the molecules throughout the volume. This produces a volume polarization, which is the sum effect of all the dipole moments. If we put a dielectric between the plates of a capacitor, the surface charge densities due to the dipoles act to reduce the electrical field inside the capacitor. So the amount of field that is reduced defines the dielectric constant K from the formula E equals E naught over K, where E is the new field and E naught is the old field without the dielectric. Since the electric field is reduced and hence the voltage difference is reduced, the capacitance is increased. So C equals Q over V, which is Q V naught over K, or K C naught. The typical value of K is between 2 and 6. So in a nutshell, capacitance increases and electric field decreases by the presence of dielectrics. Some properties of dielectrics. Here you will find the dielectric constants for some of the things that are used as dielectrics. So air, if it's used, it is 1 standard, and then the dielectric strength increases as you keep adding more and more materials. So this is a very interesting picture. So what this basically shows is that a material will have random dipoles everywhere, right? So, but once you put them inside an electrical field, that's what they do. So they align itself, the molecules of the material will align it themselves with the external field that they are placed in. So a capacitor with a dielectric will look like this. So without the dielectric, the electrical field will just be going from the positive to the negative, right? But if you put a dielectric material inside it, what happens is that this will polarize itself. So the plus of the dielectric will point towards the negative side, and the negative of the dielectric will point towards the positive side. So there will be an additional field in there. So that basically increases the capacitance of the capacitor. Now let's look at an example. So a parallel plate capacitor has plates of area 1 meter square and spacing of 0.5 millimeters. Insulator has a dielectric constant of 4.9 and a dielectric strength of 18 kilowatts per millimeter. What is the capacitance and what is the maximum charge that can be stored on this capacitor? So in this question, we are given that the plates have an area of 1 meter squared, and the spacing D is 0.5 millimeters, which is equals to 0.5 times 10 to the minus 3 meters. And we know that the dielectric constant K is equals to 4.9, and it says dielectric strength is 18,000 volts per millimeters. Okay, then it's asking me what is the capacitance. Okay, so the capacitance is going to be Ka divided by 4 pi Kd. Okay, so I know pretty much all the answers to this one. So this is going to be 4.9. I got 4.9 from the value of K. Then area is given as 1 meter squared divided by 4 pi. The regular K value is times 10 to the 9. And D is given as 0.5 times 10 to the minus 3 meters. So I plug all of these values into a calculator and I get 8.67 times 10 to the minus 8 farad. Or I can also rewrite this as 86.7 nanofarads. Okay, part B. It says what is the maximum charge stored? Okay, so the maximum charge stored will be Q equals C delta V. What is C? It is given here. That is 8.67 times 10 to the minus 8 farad. And what was delta V? It was I don't know. Huh, that's interesting. But what do I actually know? I know that V, the relationship between V and D is V equals ED, right? So what is E? E is nothing other than dielectrical strength, right? So all I have to do is figure out that this is going to be 18,000 volts per millimeter times D, which is 0.5. So 0.5 millimeters. So millimeters go away, and I get the value of V to be 9 kilowatts. That's interesting, huh? So once I have this V, I can plug that V back in here, so then I can get the value to be 7.8 times 10 to the minus 4. So Q max that can be stored on it is this number. Example 2. A neuron can be modeled as a parallel plate capacitor where a membrane serves as the dielectric and the oppositely charged ions are charged on the plates. Find the capacitance of a neuron and the number ions assumed to be singly charged required to establish the potential difference of 85 milliwatts. Assume the membrane has a dielectric constant of 3 and a thickness of 1 millimeters and an area of 10 to the minus 10 meters squared. Okay, so in this question, what it's saying is that we have a membrane and the neuron can be figured out as that. So this will have a minus charge on one side and a plus charge on the other side, right? So it will have a cell membrane in the middle, okay? And it wants me to find the C and the number of ions needed to establish delta V of 85 millivolts. Okay? That's what my job is. So first things first, C is easy. So C will be given by just the formula 4 pi kd. So that will be the fancy K, right? Dielectric constant, fancy K. And that one's given to be 3. So the area is given to be 10 to the minus 10 meters squared, right? Divided by 4 pi times 9 times 10 to the 9. What is the last one? Oh, D. So the D is given to be the thickness, which is 10 nanometers, or 10 to the power, 10 times 10 to the power minus 9 meters. So once I have all of those numbers in, all I have to do is plug them in, and I get 2.66 times 10 to the minus 13 farad. Sorry, that doesn't look like a 10. 10 to the 13 farad. Now, part B, I have to find the number of ions. Okay? What does that mean? That means I have to find total Q, T-O-T-A-L, total Q, divided by charge per iron. Okay? Now how do I find total Q? In order to find total Q, I need C delta V divided by what is the charge per iron. So if each iron is positively or negatively charged, what is the charge per iron? It is going to be 1.6022 times 10 to the minus 19 coulomb per iron. Once that is established, how do I find C? Well, C I found in part A, which is 2.66 times 10 to the minus 13. Delta V is given to us because that's what we need in order to establish it. Volts divided by 1.6022 times 10 to the minus 19. This is C, coulomb per iron. I don't know why it looks like an E, but it's a C. Okay? Per iron. Plug those numbers into your calculators, and I get 140,000 irons. So that's how many irons are going to be needed to establish this little tiny voltage.